Kia ora koutou, ko Daniel Wilson, tōku ingoa. Welcome back from lunch. It was great to see the sessions from Albert and Paul this morning. Great background knowledge. And also hear some of the part-time vocabulary coming through. We're hoping to get into that a bit more in this session. Now we've got this great context behind it. So this session is the Wānanga part of the afternoon. We're split into a couple of parts. So we've got, first off, we'll have Kiri giving a bit of an intro to our strand of the Decolonising Technology project. And then Paul Brown will be giving the details of the framework that's in a draft mode at the moment that we're wanting to sort of get your steer on whether things are looking right, what's missing, what might not be in shape, what are the concerns, get you able to input and shape this. So the Decolonising Technology project is pretty broad. There are 3 strands, and we are on the decolonising algorithms strand. So some of the part that's come up around data systems and algorithms. Obviously, everyone's primed for digging into some of this. We've got a number of team members around the room. You might want to all stick your hand up and wave. Ivy, Paul, Danny, Maui, Big Boss, Natalie, Titaka somewhere, Kiri and so forth. Kiri time. All right, I think I'll hand over to Kiri, and she'll give a bit of an introduction to what we've been up to.
As Daniel kind of mentioned, I've been tasked with giving a little bit of an introduction about our team, part of the Decolonising Technology project, looking specifically at decolonising algorithms. And then Paul's going to do the amazing work of giving this fantastic presentation to start our conversation off for the afternoon. So Daniel's kind of indicated around the room where members of our team are, but generally speaking, we come from really diverse disciplinary backgrounds. So we've got data scientists from Nicholson Consulting, we've got statisticians, we've got people working in the kind of technology space, and then you've got people like myself who wonder how I stumbled into this area. I'm a social scientist by background. My PhD looked at Māori data sovereignty and really thinking about that sort of storing data sovereignty. What are the stories held within data? How are we represented within data sets as Māori? And I think one of the really interesting things that has come out of our diverse disciplinary backgrounds are the conversations that we've got to have around kind of languaging. Paul mentioned earlier around the frustration that can arise when people will use terms interchangeably. Is deep learning the same as machine learning or artificial intelligence? And I think that was something that really came through in our early formative discussions around what is an algorithm. We were kind of trying to refine our assessment framework, which we'll get to talk about later today. And it became really clear that because we all come from different sort of spaces, disciplinary backgrounds, we weren't all talking about the same thing when we were discussing algorithms. So we had some kind of quite narrow framing that was really around the computational system. And that makes it really hard to kind of consider the systemic stuff, right? All the important stuff that goes into the ideation phase of algorithm development. And then at the other end of the spectrum, we had some more kind of broad definitions of algorithms which really looked at, well, everything is connected and bad data and bad outputs, come out. And that is equally difficult to create an assessment framework around because it's so broad. You're not then just tackling algorithms and their development, you're tackling you're tackling embedded sort of systemic structural issues, which we hope to have some impact on, but we certainly can't radically overhaul a system with our framework. So what we settled on then was a working definition of an algorithm, which was in the overview papers that were sent out to everyone, which was, we're working with an algorithmic system, which is an iterative decision-making process that is driven by humans, data, and computational algorithms. So this really allows us to unpack as many stages of the algorithm, its development, and the values that are embedded within it as possible. And the context that we're kind of working out of is really important as well. So I think in 2018, the last kind of assessment report indicated that 14 agencies were at that time using operational algorithms, and those included the Ministry of Justice, ACC, Inland Revenue, Ministry of Social Development. The kind of list is, well, there's 14 in that list. But increasingly we see shifts towards algorithms being the way to create more efficient systems, to remove bias and all of that. And generally speaking, there's little to no involvement of Māori in these systems. And so that's where we're kind of working. But there are signals of intention, maybe, to be more inclusive and aware of how Māori are impacted. I think there was also the Trust and Automated Decision-Making report that came out, which indicated that there needed to be robust equity assessment protocols for algorithms, meaningful Māori participation in institutional algorithm self-assessment processes, and the creation of a Māori values framework and tikanga guidelines to support automated decision-making development, use, and maintenance. So that's a bit of context around where we're working from in our team. And I think just the last point is that these are not sort of final products. We are open to engagement and understanding the positions of people in the room with various kind of expertise. But I'll now pass over to Paul to give his amazing presentation. Thank you.
Pressure's on now. Amazing. It's high pressure. Okay. Kia ora everyone. Paul Brown tōku ingoa. I'm a part of the tikanga and technology group, Decolonising Algorithms. I'm currently a research fellow up in the Department of Mathematics here at University of Waikato. So my background is as a statistician. And so when I first got into this particular project, I actually found it quite hard. And Kiri touched on this about what an algorithm really is. I mean, decolonising an algorithm kind of didn't really make sense to me because I'd always thought about algorithms as just a computational function, something that is just really a list of computational procedures to generate some kind of output. But as I've come along in this project, I've realised that there's a wider decision-making process that comes along with these, that we use with algorithms. So I'll first touch on that. The other thing I wanted to say, just prior to going into the specifics of our framework that we're developing, is that there's a growing literature and a growing concern about algorithmic bias. And we see that there's quite a few different examples from facial recognition technology in the United States to recidivism risk algorithms. I do work with police from time to time on different projects, and so this one is particularly interesting, at least for me. And there's countless cases of algorithms being developed in the US, the UK, and even in New Zealand. So they're being developed, these algorithms to compute the risk of recidivism for a given offender coming through the courts. And there's evidence to suggest that there are biased outcomes when it comes to marginalised communities. So our decolonising algorithms is more a subset of this problem of algorithmic bias, because we're specifically looking at the context of Aotearoa, New Zealand, and the impacts that these algorithms could potentially have on Māori. Okay? So, decolonising algorithms, we're looking at decolonising approaches to algorithm-informed decision-making. And like we said, not just decolonising this algorithm, this computational function, but the ecosystem that actually surrounds the algorithms. So generally the inputs and the outputs. But there's a whole bunch of decision-making that goes into what inputs you put into the algorithm, and there's a whole set of interpretations about what comes out of the algorithm, the outputs. So our work involves developing frameworks, guidelines, methodologies that can identify components of this whole ecosystem where there's a potential bias toward Māori individuals, communities, populations, etc., or Māori groups. So I'll touch on this briefly, because Kiri mentioned this before, about defining algorithms. This kind of narrow conception of an algorithm that at least I had, which in this framework we've called a computational algorithm, an abstract formalized description of a computational procedure. That was a very formal description. There's tons of different definitions that all kind of say similar things. Lists of instructions that determine how programs read and process data to generate output. Me, personally, I just saw them as a computational procedure that takes in inputs and spits out outputs. But I've kind of extended that a little bit further for what we call an algorithmic system. So the inputs, like I said before, are based on a whole bunch of decisions that humans have made prior to it actually going into the algorithm. And then the outputs are then generated and then interpreted by whoever's interpreting them. So we've defined this notion of an algorithmic system, an iterative decision-making process that's driven by humans, data, and computational algorithms. Just looking at the computational algorithm itself is a little bit boring in terms of what we really want to analyze here. It doesn't really capture what the real problems are with algorithmic bias. So this is our conceptualization of an algorithmic system. You can find this on the paper, and this is something that we'd really like to get your feedback about, because we all work with algorithms in different contexts and different spaces. So it's really interesting to kind of understand how everyone conceptualizes an algorithm, and then kind of weave that into our framework. So let me just take you through this, what we've called an algorithmic system. We've got these different, what we're calling components of this system, and it kind of starts with some motivation. There's some problem or some goal that we want to achieve, and we've decided, or someone's decided, that we're going to use data and algorithms to actually achieve this. Now this motivation, this purpose, these goals or problems may lay outside the algorithmic system at first, right? That's why you've kind of got the motivation component a little bit outside of the whole process. So first we discover or we define a problem or a goal, and then we ask some questions about it. The important questions that we want this algorithmic system that we're going to develop or that we have developed, what questions do we want answered? And then from there, you design some kind of study or some kind of research. You have a look at what data you're going to need for this, what variables, what kind of computational algorithm you're going to need for these different types of data sets. And so you make these decisions, and that's all encompassed in the design component. Then we get into the general algorithmic functions here. We take the inputs that we have, so we've decided on what data we have and what data we're going to use. What model we're going to use, computational algorithms, and we're going to dump it all into the algorithm. Okay, and then that algorithm is going to generate a set of outputs, and those outputs are then used to make decisions about the original motivation or the original problem or goal that you want to achieve. So this is kind of how we've conceptualized this algorithmic system. And a few things. I mean, if anyone is actually, when they're developing algorithms, it's not a linear process like this. It's not like, oh, yes, I'm just going to go straight down the list and then we're done. That's not how it works at all. It's an iterative process. Generally, you'll have your inputs, you'll chuck it in the computational algorithm, and you'll realize that it doesn't run properly, or outputs that is generating nonsense. So then you're like, oh, let's go back to the drawing board. It's not a straightforward linear process. It's an iterative process. So some of these components are dependent on other components. There's also questions that you want to ask with respect to the whole process as well. Things like who funded this process, who's involved at what stage, implementation. Actually, this process component can be asked, you can ask questions about the process all throughout the development of this. Okay, so that's kind of our conceptualization of this algorithmic system. So when coming up with this framework, what we did was we said, well, look, we could break this system down. I should add that we didn't just do this at first. It took a few iterations ourselves. Right? But when we came up and we were happy with this conceptualization, we thought, well, look, here are the main components. Here are the stages of the development of this algorithmic system where you could potentially get bias creeping in, where things can go wrong, where consultation is not sought, all of these different issues. So the framework that we developed was basically around these different components of the system. So really questioning and digging deep into each of these parts. And then, coming up with questions, we needed some kind of guidelines, and what we've done is we've kind of used some of the ideas from the multi-data sovereignty, Manamaki framework principles, so the MDA, multi-data sovereignty principles of rangatiratanga, whakapapa and whanaungatanga. That's ideas around the governance of data and then the use of data. But of course, we're now in the context of algorithms, okay, not just data. So we've kind of used these as guiding principles to frame some of our questions. So going through the process, I'll take you through it fairly briefly, but of course, feel free to read the document that we've sent, and I think it's on each of the tables as well, if you're interested in the actual questions that we're asking. So, the first component here, the first hokonga, is the process. understanding the algorithmic system as a whole, and this includes questions to be asked before the process begins, during the process, and perhaps even after the process once you've developed things. But then, not all algorithms just stop, right? There's always constant development of these things, especially if your algorithm is taking in new data all the time. So the different types of questions we ask here in the framework, I mean, the big important questions are who's involved in terms of development, in terms of funding, in terms of who owns the rights to the algorithm and the data as well. Where and what purpose? So, does multi-involvement occur at any of these stages? Has consultation been sought, etc.? So questions surrounding those issues. Relevance and intent. Is the overall process relevant to multi? Does it contain multi-data? Is it an algorithm whose outputs are directly going to affect multi? If not, then that's fine. But if so, then we really need to make sure that this algorithm actually works for multi. Serving multi aspirations, does it ensure equitable outcomes? And then going through the process. I mean, when you're developing an algorithm, sometimes there's an implementation stage, right? You've got a proof of concept, you know your algorithm, your computational algorithm works, it gets the outputs you desire in a test case. Now we want to implement it into a wider system. So, how is the process implemented, maintained, and monitored? And especially in the monitoring phase, as you're taking in more data, if there's problems with the data, you might end up perpetuating systemic biases within the data set itself. So who's monitoring that? Right? Who's maintaining the data so that hopefully you don't have bias in your data? All of these kinds of questions. The second and third components here of the questions that the motivation generates. The second component, the motivation, and third component, the questions. The questions that are generated through the motivation of the problem. So we want to understand the problem or goal that the algorithmic system is trying to achieve. So that's really the key part about the motivation. So the questions involved: what is the actual problem or goal that you're trying to achieve? Does it have any relevance to multi? And then we go into, who's actually framing these questions? Whose perspective are they really from? Do multi have any say in the framing of the problems or goals that you're trying to achieve? And another big question is, actually, should you be using an algorithm to solve this particular problem or goal? I'll give an example shortly on space-time modelling of burglaries in Hamilton. That it's probably a relevant question to really ask. The third is the questions that come from the motivation, and really that again is making sure that things are consistent with the questions that you're trying to answer. So do your questions align with the motivation, the problem or goal that you're trying to solve, and who's involved with this process of defining these questions. The fourth component is the design, so understanding the design of the algorithmic system based on the researcher's framing of the problem and research questions. So again, is a quantitative analysis here appropriate? Then you get into data collection, data storage, all of these kinds of issues with data, because this is really where you start collecting and thinking about using the data and what variables that you're going to use in your model. So what are these data collection processes? Relevant, is it representative of the population? Proper sampling techniques, are they chosen? I'm a statistician, so I always get on my high horse about how you collect data. Got to be probability-based random samples, right? And I know that's not typically the case, especially when you're just getting data from, I don't know, Google or something. It's not typically representative of the whole population, just the population that use Google, which admittedly is quite a lot. But, you know, sometimes when you're getting data out of databases, there could be problems with the fact that you're trying to represent a certain population, but you don't have the data to actually do so. So, you know, data issues again that crop up. Potential limitations, have they been outlined? And then there are techniques, especially in statistical random sampling, where you can get fair multi-representation in the data set, things like stratified random samples. Are these things being used? And then there's the issue of governance of the data, especially with regards to ownership, and then you've got the mahi side issues of storage and monitoring, all these things. So if you have multi-data, or if you have a data set where multi-data is present, are the principles of multi-data sovereignty being upheld? So appropriate procedures for storage, governance, etc., and use. So we've got questions pertaining to those issues in the framework. Now we get into what I think is the interesting stuff, the inputs, the outputs, and the computational algorithm itself. So we want to understand the inputs that are fed into the machine to generate outputs used for decision making. So the types of questions here, again, data, representative sample, multi-data, and then you've got some of the more technical aspects of things. A lot of data sets, some of the data sets that I've used, have quite a bit of missing data and incomplete data sets. How do you deal with things like this? Well, in statistics, a lot of the time we use imputation techniques to kind of understand how the data is distributed and then generate some kind of synthetic data set. But are these methods appropriate in certain cases? Especially if you're trying to generate data about molding, which some might have tried with regards to the previous census in 2018. But in any case, so yeah, you've got issues of reputation, individual level data, or community data, issues pertaining around those. You've got, also in the inputs, you've got choices about which variables you want to put into your model or your algorithm. And also the different types of models. You know, Albert talked this morning about the different types of machine learning algorithms and the different types of models that you can do, things like random forest, things like clustering, k-clustering means, nearest neighbors, all of these kinds of things. So what are you choosing here? Or are you going to go more complex and do deep learning? I mean, all of these things can be done, but there are issues involved with these that I'll touch on a little bit later. Are your models relevant, and what are your assumptions? Again, from a statistical point of view, when we create a model, we put in quite a few different assumptions into this model because we're trying to recreate the real world with incomplete information because we don't have all of the data. We might have a lot of data, but we don't have everything. And of course, usually a model is just some kind of additive model. This factor plus this factor, etc., doesn't necessarily represent the real world. So what are your model assumptions here, especially as they pertain to modelling? There are other inputs that you can also critique here, such as the use of weights, such as the use of priors if you're a Bayesian statistician. There are these inputs to consider as well. So that's more on the technical side. And I can appreciate that sometimes this steers it away from issues of Māori to just issues with the inputs, right? But they're all pretty relevant because they all affect the outputs at the end. And the outputs are what we use to make the decisions. The sixth component here is the computational algorithm itself, understanding and deconstructing the computational algorithms that generate outputs from inputs. So questions really around the development and design of the algorithm and if it's appropriate with the type of data that you have. Again, in the development stage, is multi-consultation sought if it's relevant, which it usually is. And then algorithmic choice. Like we said, there's a ton of different algorithms out there, computational algorithms. Why that particular one? Does it have some kind of advantage over others? Is it just out of computational, is it just because it's computationally feasible to do it with this particular algorithm and not with another algorithm? The last two components are the outcomes and the decisions that are made from the outcomes. So in the outputs, in the output component, we talk about the outputs themselves, measures for accuracy, because like I said, if you've generated some outputs that are not accurate, and then you go ahead and use them, well, they're just going to be terrible. So what are the measures of accuracy that you are using, and how do you measure the impact on Māori? And how are inaccurate outputs dealt with? The big part here, though, is really the analysis and interpretation. Who is interpreting these outputs? Again, I'll show you an example of an output. I could interpret it one way and make a decision. You might interpret it another way and make another decision. So who's involved in the analysis and interpretation? And there's, actually, I forgot to mention in the other components as well, is there's opportunity for capacity building. I get told a lot that there's not a lot of Māori in certain spaces within maths, statistics, AI, which I think is generally true. But then sometimes there's, with the development of some of these systems, there's opportunity there for capacity building for Māori, which are part of the NBS principles. So there's capacity building and a multi-perspective sort in the analysis and interpretation of the outputs, and then understanding how decisions are made from that point on. So who actually has ultimate power in taking these outputs and implementing it into policy or into some kind of decision. So who's really involved in that process, and how are benefits and risks managed from that point on. So that's a general rundown of the framework. What we hopefully will get today, or what we'll ask everyone to do, is if they've got any kind of, or any suggestions on things that we may have missed, or things that you think are good, things that you don't think are good, you know, we'll have this workshop shortly, so you're welcome to give your feedback there, as well as our overall conceptualization of this problem. So let's just reinforce things with an example on burglary modeling. So there's this model that is currently in development. I know because I'm the one that's currently developing it. That uses recent crime data with several model assumptions to predict future hotspots of crime. The crime that we're talking about here is residential burglaries, though I'm currently looking at other different types of burglaries, but mainly burglaries. That's breaking and entering into homes. So trying to predict what might happen next week or at the next step of time. The intention for this from the police's point of view, even though I should add that it's not funded by police, is that they want to take a more preventative approach to policing. Okay? So if they can understand patterns of behaviour of crime, then they might be able to stop it before it happens. Okay? Leading to safer communities, great, though can cause other problems, which we might talk about shortly. But that's the intention here. Okay? Now, they gave me some data, and that was cool. So the data is locations, northings and eastings on a map, where we can plot it, and then we can implement some model that that takes 8 weeks of data and then tries to predict in the 9th week in terms of hotspots. Now, the computational algorithm, I want to briefly just mention this. It uses an algorithm called INLA. I don't expect anyone to have heard of it, unless you're a keen Bayesian modeler. But it's called Integrated Nested Laplace Approximations, and it's actually a tool to perform fast Bayesian inference for fairly complex models. I won't go into the history of Bayesian, but there's another algorithm that just takes ages to run, and in practical terms is no good for models like this. So that is the computational algorithm that we are using in this case. It is a very technical algorithm. Took a long time to actually understand, and that could lead to problems when doing the analysis. So we did the analysis. Oh, actually, first, I'll just mention that these are the kinds of maps that it generates. So you've got Kiri here, you've got the river, you've got the lake, and you've got some model fitting of the intensity of burglaries. So what it will do is it will give greater intensities in red around clusters of burglaries that have happened in near time. So there's a couple of other things that this does really nicely. One of them is it takes the river into account. So the theory is that if one place gets hit on the map, then the others, houses surrounding it within maybe a 400 or 500 metre radius, are more likely to get hit next week. And then that correlation, that dependency, falls over time and space. And this is a well-known criminology theory called the near-repeat theory. But what it does is that these radiuses don't, or radii, sorry, plural, don't extend where you have physical features like a river. So there might be a radius this large, but because there's a river, you don't expect someone to swim over the river and try and do some bad things on the other side of the river. So it has some a few different complex ideas in this model when it does the prediction, which looks something like this. And it's just the red spots are where you're more likely to get hit next week. The black dots there are what actually happened in this particular example. I mean, we've got a year of predictions here, but this is just one particular one. I like this one because it actually shows on this hotspot map here, you don't see the hotspots flowing across the river unless you're at a bridge. So this one on the right hand side there. So you can see kind of that in motion. So, this is fairly cool, a nice application if you're interested in safer communities. But, putting it through our frameworks, there are a few problems. So the biggest thing, I think, is that there was no Māori community consultation here. I mean, I'm Māori, so that's fine, but I don't claim to represent all Māori, especially Māori in Hamilton. So there should be some community consultation about this quite an important issue. The real problem here, that at least from my point of view, is that you've got these hotspots that determine crime, that predict crime. So, you could send police cars out there, and then you get problems of over-surveillance in certain areas, and also can cause feedback loops. So you're picking up crime in these particular areas, but not in other areas. So then when you put that back into the data set to predict next week, you're just going to perpetuate that kind of bias there, which is a real problem in predictive policing software around the world. And that, of course, leads to negative outcomes in terms of community and how they view police, etc. So potential for negative outcomes, especially with over-surveillance of areas where a high proportion of Māori occupy. Just as bigger issue of Māori is really class. Potentially, you're going to predict more where there are poor areas, and that's a real problem too. And that comes to the fact that it's really hard to just isolate one particular thing like ethnicity, because it confounds with other variables. Now, I haven't used in this model ethnicity. I haven't put anything in there, but I'm using space. Okay? And space can act as a proxy for all sorts of things, including ethnicity, including class, including students, a lot of things. Okay? So that is a potential problem using this particular variable of space. But then again, you can't draw a map. You can't do these mappings without the spatial feature in here. So you've got, it's tough. It's a tough issue to solve. In fact, if anyone can solve the issue of confounding variables, they'll win a Nobel Prize or something. It's that big. Okay, so one thing about this is a Bayesian model, like I said before, and involves the use of priors. Now, priors are basically opinions or a subjective position that you take on a certain parameter. And there's two important parameters here, including correlation range and the time, how correlation is affected over time. I put my priors in here, what I believed, but my belief was based on American studies. That could be a problem because patterns of crime in Aotearoa or even in Hamilton, Kiriroa, will be different from those experienced in America. And one major issue is that INLA is a complex algorithm and takes a long time to actually learn. So you have explainability issues. With regards to recidivism risk or reoffending rates, a judge might use this decision support tool. So it uses some complex algorithm with all this data, and it predicts reoffending. Okay, cool. So the judge says, reoffending, you're either going to stay in prison or go to some, whatever. But then the offender asks, well, how did you actually come up with that decision? What's the judge going to say? Well, the judge is probably a very smart person, but they are not algorithm developers, they are not statisticians, they're not data scientists. So you've got problems with explainability. In my opinion, my colleagues might think different, but the biggest problem that we've had so far is actually getting our hands on some algorithms to test the framework. The main reason is because a lot of algorithms are proprietary. They are considered by some, especially in the corporate world, as trade secrets, so they're not exactly going to give us their algorithm to analyze, right? So there's sometimes a lot of transparency issues that come across, and one might think that there's a transparency issue here just due to the fact that the algorithm is very hard to explain. One thing about this particular example is that it's not actually implemented as an algorithmic system. And what I really mean by that, I mean, it's an algorithmic system, and it's how it is, but it's not implemented and used. So we're not using it right now to make, well, the police or me are not using it now to make any particular decisions about policing strategies. But there are potential problems that could come about if this is implemented in real life. So who's going to monitor the system? I'm probably going to be too busy to do that. So is this going to fall to a job, if it is implemented, by the way, of someone with the relevant expertise and the awareness that of the problems that this model could actually perpetuate. So that is a potential problem there. Of course, capacity building, can we get more Māori involved? How are the maps to be used? So I can give some kind of presentation to the police on how I think they should be used, but of course they're going to have a very different idea, and they're the ones that are going to be using it in the end. Which actually adds another question, like what's my responsibility here as well as the developer of this model? But anyway, surveillance or insights, I mean, will they use it for surveillance? Or will they actually say, well look, we've got insights into where the problems are. Are there alternative policing strategies? Can we actually get some community involvement with police here? Or some community interaction? Some kind of different strategies, not just let's chuck a policeman there to patrol the area. And yeah, proper training needed for police to manage the system, interpretation of the outputs, etc. So that is our rundown of the framework and an example. You're more than welcome to read our draft documents. Like Kiri and Daniel said, we've got a fair bit of refining to do, and that's kind of what we're hoping to get out of the session after this. Just some feedback on what you all think. Other future work, and I've put this in the order that you see above, but really it's kind of the opposite. Tataka mentioned in his opening this morning about, okay, we've deconstructed this algorithmic system, right? How do we build it back up into an indigenous system? So indigenizing the system after you've deconstructed it. So taking this kind of decolonizing, indigenizing approach, something a little more positive. But actually doing that and developing a framework, we have some ideas. Actually, our social scientists have better ideas than, well, a couple of good ideas that we could build off. So that's one thing that we're hoping to do in the future. Second is an audit tool for algorithms. So it's all good us doing this framework, but we really want it to be used. So once we've kind of defined things a little more and developed the frameworks, how can we make some kind of tool for developers to use so they can actually be aware of these kinds of issues? I mean, a lot of the algorithm developers or algorithm system developers, AI systems developers are not Māori. So we're kind of hoping that we can shine a perspective for them to kind of use our tool here. So some kind of easy to use tool that would be really nice to develop. And third, of course, is the refinement of the framework. Now, there's two things that we really need to do. One is test the framework with more algorithms. And I'll put out a plea to everyone in the room now. If you are developing an algorithm or you're using an algorithm and you have the information that is necessary and you want a level of scrutiny in terms of the issue of algorithmic bias with respect to Māori, we're more than happy to do that for you. So yeah, if there's anyone out there, or if you know anyone, that we could use your algorithm or these algorithms to test our framework, that would be great. And of course today, do you think we're missing anything? Do you think we've conceptualized things correctly, incorrectly? Do you think we could refine things more? We'd love to get your opinion on it. And that will help us in refining things further.